These notes summarize the portion of Chapter 11 of Modern Chemistry that talks about gas laws. This chapter expands on what we learned about gases in the previous chapter and puts the mathematical twist on it. So it's going to be all about mathematically manipulating three primary variables, namely the variables that deal with pressure, volume, and temperature. For our purposes, pressure will typically be in units of atmospheres or pounds per square inch, or millimeters of mercury, which is the same thing as torr, and there are a couple of other oddball units, but those are the big ones. Volume, if you remember, can be measured in liters or milliliters, which for our purposes will be the same thing as cubic centimeters, and so on. And finally, the trickiest one is temperature. In science, you know that we use the temperature degrees Celsius typically. The problem is mathematically degrees Celsius don't behave properly. We will have to convert the temperature in Celsius into something called Kelvin. And the reason for that is that Celsius is an arbitrary scale. We assign a value of 0 degrees Celsius coincidentally to the point at which water freezes, and again coincidentally we assign 100 degrees Celsius to the point at which water boils. The Kelvin scale has the same sized units as the Celsius scale, but it has what's called an absolute zero. And what that means is we can actually go down to an absolute zero temperature below which you can't go anymore. See, on the Celsius scale, you can make ice colder than 0 degrees Celsius. There is more heat that can be taken out of the ice cube. But on the Kelvin scale, if you get all the way down to 0, there is no more heat to be removed, and that's why it's referred to as an absolute zero. So all temperatures for our calculations given in Celsius must be converted to Kelvin first. And a quick recap of the work you've already done on learning about pressure units. So if you remember the information from the video on how barometers work, then you'll remember that 760 millimeters of mercury is the height of a column of mercury that's supported by the weight of our atmosphere. That's why we can use it to measure atmospheric pressure. All these other units are equivalent, so 101.3 kilopascals or 101,300 pascals is the same thing as 1 atmosphere or 760 millimeters or 760 torr, etc., etc. And for volume, we typically use milliliters or liters. We may use the equivalent of milliliters, which would be, again, for our purposes, cubic centimeters. There is a very slight difference, but we're not going to worry about it. And if we're talking about atmosphere, for example, we may actually use cubic meters because gas is so is not very dense, so we typically look at huge volumes of it. Again, Kelvin is what's known as an absolute zero scale. And because it has an absolute zero value, that value is 273 degrees less than the freezing point of water. It's minus 273.15 degrees Celsius. We won't worry too much about the 0.15. So to convert from Celsius to Kelvin, we're going to have to add 273 degrees. And of course, the opposite is true. If we're given the temperature in Kelvin, we're going to have to subtract 273 degrees. Notice that we don't use the degree symbol for Kelvin the way we do for degrees Celsius. We don't say degrees Kelvin, we simply say Kelvin. And again, the temperature minus 273 Celsius is referred to as absolute zero. So before we get into the specifics of the math of all these three variables, let's talk about a refresher on the kinetic theory of gases from the previous chapter. Remember that an ideal gas is one that subscribes to all of these rules of the kinetic theory, namely that the particles are far apart relative to how big they are. Any bouncing around that they do, either off the walls of their container or off each other, is something referred to as elastic. That means they're not losing any energy. Kinetic energy is conserved, is how we say that in physics. Gas particles are in constant motion. There are no van der Waals or Other weak forces of attraction, we ignore those. Every gas particle is kind of its own little entity. And then finally, we can measure the temperature of a gas, and that gives us a measure of the average kinetic energy of those molecules. Remember, kinetic energy is the energy of motion. A gas put into a container will expand to fill that entire container. Gases, like liquids, can be poured from one container into another. And remember, this property of fluidity applies to both gases and liquids, and it's because the individual molecules or atoms are not bound to each other. They're not frozen in place the way they are in a solid. And of course, low density. Because there's a lot of space between and among all of the different molecules or atoms, there's a relatively little mass that's put into that space, and that's why it has low density. Compressibility. Gases can be squeezed or squished into a smaller space. If you've ever pumped up a bicycle tire, you know exactly what this means. You're cramming more and more air into the inside of the tire, and of course that increases the pressure so that the tire gives you a good spongy but solid surface to ride on. Given enough time, the random motion of gas molecules will mix two or more gases together through a process called diffusion. And gases can go through tiny little holes, and that would be called effusion. Real gases do not behave like ideal gases, so there are some exceptions to how they behave in terms of the kinetic molecular theory. But we can approximate ideal conditions by having either relatively low pressure or high temperature. And finally, the more polar a gas is, the less ideally it behaves. And that's because if you remember, polar molecules have one end of a molecule that's positive, one end that's negative. And of course, that negative end of the molecule is going to be attracted to the positive end of some other molecule, and you will have attractive forces that basically can't be ignored. So the more polar a gas is, the less ideally it behaves. We'll be using the term STP, and that simply stands for standard temperature and pressure. And the standard conditions for STP for temperature is 0 Celsius, 0 degrees Celsius, and standard pressure is simply 1 atmosphere or its equivalent, 14.7 psi or 760 torr, and so on. All right, so getting into the math part. Gas laws show the relationships among the three variables: pressure, temperature, and volume. Some of the times we're going to keep one of these things constant and see how the other two behave, or keep a different one constant and see how the remaining two here behave. Although the relationships between two given variables are given various names, you will not be responsible for memorizing the names and what variables they correspond with. Remember, we have three total variables: pressure, volume, and temperature. And this particular relationship between pressure and volume occurs when temperature is held constant. Later on, we'll see how to treat this when all three of these variables are combined together. Similarly, a second law relates volume and temperature when pressure is held constant. And of course, a gentle reminder that anything we do with temperatures in these mathematical problems must be in Kelvin. So if they're given to you in degrees Celsius, they're going to have to be converted into Kelvin first. And finally, the relationship between pressure and temperature when volume is held constant. And again, Celsius temperatures will have to be converted into Kelvin. So instead of using any one of those calculations individually, we actually can combine them into one equation called the combined gas law, combined for obvious reasons. It includes all three of the variables. So if you go back and look at those descriptions of the three different equations, you see that in all of them, one of these three things is being held constant. Okay, so if temperature, for example, is being held constant, you can see that T1 and T2 are going to be the same. If we're not changing temperature, they're going to be the same, and those cross off, and you get P1V1 equals P2V2, which was an example of one of the laws. So we don't have to start with P1V1 equals P2V2. We can always start with the combined law and then just cross off whatever we're holding constant. So the remaining set of slides is nothing more than example problems. I invite you to go through the next couple and kind of test yourself on them, and then go ahead and start working on the assigned homework. I find it helpful to label the stuff in the problem statement with the various variables. So we're going to call our starting condition 1, use a subscript 1 for that, and our ending condition 2. So we're told that a sample of oxygen has a volume of 150 milliliters. So I'm going to call that my initial volume, 150 point, right, 3 sig figs. And its pressure is 0.947 atmospheres. I'm going to call this P1. What will the volume of the gas be? So that's our unknown. V2 is going to be our question mark. At a pressure of, so that's our second pressure. So we're going to start with the combined gas law, and we're going to write the whole thing down. So P1V1 over T1 equals P2V2 over T2. In this problem, there's no mention of temperature. So let's assume that the temperature is constant, T1 equals T2, and because it's the same on both sides, they both cancel out. And we're left with P1V1 equals P2V2. Now, I like to rearrange my equation so it looks like this, and then substitute the variables in there. Students usually like to put numbers in right away. So I'll do it your way for this one, and I'll do it my way for the next one. So here's your way. And this is absolutely fine. The math works. It doesn't matter whether you set it up like this first and then solve, or do it the way you guys typically do it. Okay? A couple things. Make sure that the units are the same. So the two pressure units are both in atmospheres. If they're not, you're going to have to convert one of them. Okay, they must be the same. And of course, because the initial volume was in milliliters, your final answer will also be in milliliters. Now, a quick gut check. What happened to the pressure? We went from 0.947 to 0.987. The pressure went up. We increased the pressure. Can you visualize how you're maybe squeezing a balloon and making its volume smaller? Does it make sense that it should be smaller? We start at 150 milliliters and we wound up at 144 milliliters, so that kind of makes sense. It's a quick kind of gut check. Let's take a look at another one. So I'm going to pause and give you a chance here to do this one on your own, and then come back and see if we got the same thing. So here's my solution. Remember, double check to make sure that the units cancel appropriately. They have to be the same. Also notice up here that the fact that the balloon rises to this, it wasn't 6.5 meters, it was 6.5 kilometers, sorry about that. That information is irrelevant. It doesn't go anywhere into the equation. It just tells you that this balloon went up in the atmosphere, and because the pressure is less up there, the volume actually expanded. Notice what happens here logically. The pressure goes down to half of what it was originally, and the volume winds up doubling. You'd say that they're inversely proportional. The rest of these I'll go pretty fast through. So first thing here, I want to label my variables and double check to make sure the units make sense. So I have my 2 known volumes and 1 known pressure. I'm solving for the remaining pressure. There's no mention of temperature, so we're going to assume that it's constant. And then I'm going to rearrange to solve for P2. And finally, substitute and crank out the answer. With this type of problem, notice that we're talking about volume and temperature. Okay, we're going to start with the same equation that we did, the combined gas law, and then we're going to cancel out pressure because nowhere in there is pressure mentioned, so we're going to assume pressure stays constant. Also, a reminder that these guys need to be converted to Kelvin. you have to add 273 degrees. Start with the combined gas law and then cancel out, in this case, pressure. And then solve for whatever you're looking for, V2. Make sure you're taking your time when you're manipulating these variables and bringing things from the denominator to the numerator and so on. Okay, if you're not comfortable doing it this way, that's fine. Go ahead and substitute the numbers in the way you normally would, and then rearrange the way you need to. So again, label the variables. Remember to add 273 to the Celsius temperature, and then set up and solve. Now, if the problem doesn't specify what units to have the temperature in, it's perfectly fine to leave it in Kelvin like this. But if the problem, for example, had said, what is the outside temperature in degrees Celsius, then we would have had to back out the 273 degrees, and you'll see we actually get a negative value here. For this problem, we're holding pressure constant, so the pressure cancels out again. Notice that this problem actually asks for the temperature in Celsius. So when we get the final answer for T2, we're going to have to convert it back into Celsius by subtracting out 273. Notice in this problem, the volume is held constant. The volume of the can doesn't change. It's just the temperature of the can as well as the pressure that's inside of it. So we can right away cancel out the volume. And again, rearrange and solve. Don't forget to convert your temperatures to from Celsius to Kelvin. Pick out the variables. Remember to do the math in Kelvin. And then subtract out the 273 to convert it to degrees Celsius. So here's an example of a problem where nothing is being held constant. You see that the volume changes from 50 liters to some unknown volume. The temperature changes from 298 Kelvin to 283 Kelvin, and the pressure is changing from 1.08 atmospheres to 0.855 atmospheres. So we start with the same equation we always use, but this time we don't get to cancel anything out. The good news is that the approach is still the same. We're going to isolate the variable that we're looking for, namely V2. We're going to put P2 and T2 over on the other side. It's going to be messy, but it's going to be pretty straightforward. A quick double check shows that atmospheres cancels out top and bottom, Kelvin cancels out top and bottom, leaving us with just units of liters, which is appropriate for a volume. When you read this problem, you'll notice that we're given a volume, but we're not given any temperatures or pressure to begin with. It's actually buried in this phrase here. Do you remember what STP stands for? Standard temperature and pressure. So that tells us that the temperature that we're starting at is standard temperature, which was 0 degrees Celsius or 273 Kelvin. And the pressure is going to be standard atmospheric pressure, which is either 760 millimeters or 1 atmosphere or 14.7 psi. The trick here is to look at what they're asking for pressure down here. They're looking for it in pascals. So we're going to use the initial temperature, atmospheric pressure, at 101,325 pascals.